Okay, let's start. Um, my name is Ivan Yushkevich, and today I try to tell some words about the research that was made. Something about me. I'm working as a security auditor at a digital security company, do some random security stuff, and so on, and blah, blah, blah. Okay. Passwords are one of the cornerstones of security. They are just everywhere. Laptops, banking accounts, Wi-Fi, even coffee maker may require password for its working. Every maybe months there are some news that some maybe popular site are hacked and its database with users and password are sold all over the internet, and it always very popular news. So when during pen test you get access to some passwords or user accounts, it's always the good sign. How they can be stored? First of all, clear text. So you somehow get access to the database using SQL injection, for example, and that's all. So you can use this data right immediately to access other servers and services. They may be encrypted. So before previous part, you must find the key, but in most cases, all the encryption is just base 64. And in most cases, instead of passwords in clear text, you got hashes. There are some features about hash functions. First of all, avalanche effect, that if we slightly change data, the output will change significantly, and it's one-way functions. So we can easily compute output from the input, and but to get input from the output is nearly impossible. So during pen test, you somehow get access to credentials using ARP, NetBIOS, or whatever spoofing, or get access to the server and got shadow file. So you got passwords not in clear text but in hashes, so you need them in clear text before the using. On this slide you can see the most common hash types that can be met during pen test. It's different crypt functions for Unix systems, NTLM, NetNTLM, even keypass databases can be found on file servers where IT administrators left them for backup. There are some methods that can be used to recover passwords. I try slightly to describe all of them with their pros and cons in my own opinion. First of all, rainbow tables are used to recover passwords for certain lengths and certain char set. They take less processor time than brute force and less disk space than table lookout, but still no cell support. And the most modern hash algorithms add random string for password before it's hashing, and they also take pretty much time and space. And one of the main drawback that the rainbow table that is calculated for NTLM can be used for cracking MD5. Another method, brute force. The idea is rather simple, I think. So we take a word, calculate hash from it, compare with our input, and if they are the same, we got the goal. If not, we consequently change one letter and do it again and again. There are a lot of types and methods to do such things, and one of the main benefits that it can be done on CPU, GPU, even using cloud computing, for example, Amazon Cloud. And other main benefits that with using such methods, the passwords will be always found, but the question is when. So if you try to crack NTLM hash for passwords that are nearly 12 chars lengths, and this can really take a lot of time using brute force. Another method, popular method, is wordlists. The main benefit is that they are small and have good efficiency. So on this slide you can see the graph with the results of cracking some hash lists with wordlist attack and brute force. As you can see, wordlist attacks allows us to recover 3 or even 5 times more passwords for the same time than the brute force. But the main drawback that if passwords are not in the dictionary, it will not be recovered. So yes, there are some methods to mutate word, but this is a common case. So okay, this was common methods, and after that I try to do some tests. I pick up hardware that I have. It's a typical laptop GPU card, it's NVIDIA 610, more powerful one that can be used for cryptocurrency mining and can run most modern games on high settings, and 2 CPUs, also a laptop one and more powerful desktop version. On this slide you can see the speed results for brute force for cracking passwords that are 6 charts lengths and contains only lowercase and numbers. As you can see, only for MD5 and NTLM, only MD5 and NTLM requires acceptable time for cracking. But such options will not be met in the real life. And even with such options, hash algorithms like crypt or others that have some strengths to brute force attacks requires a lot of time even using GPU. Another simple test is dictionary attack. Or at least. For this I took RockU dictionary that contains about 14 million of passwords and tried to do some tests. As you can see, all seems fine. But this is right only for one hash. And if we got a bunch of them, even powerful GPU will require a lot of time for cracking. And I should say that RockU dictionary is really good, but not the best one. So let's make some problems. First of all, during the pen test, for example, I somehow get credentials and I'd like to crack them right now and to use the clear text passwords to get access to other servers and data. And if I can't do so, I send them to powerful rack station or brute force PC. So the time is really critical for me, and I should pick up some methods that have much efficiency. So, and what about the hashes I got? They all contain cells, so I can't crack them with rainbow tables, and also I got solid state drive and have no disk space for them. And they are really hard to recover. And rely on this, depend on the speed test. The most optional way is to use wordless attacks. But we need to pick up the word list that might have some features. Like it must be small and can be downloaded easily and stored on the hard drive with no problems. It must be useful, so it mustn't contain something trash or others, and can be used using rule-based attacks. There are really a lot of word lists all over the internet. So how can we choose the right one? First of all, to make this we need some information about the dictionary. What this information can be? First of all, what kinds of words does the dictionary contain? Maybe some length distribution, if these passwords are names or maybe keyboard combinations and so on. Is it a junk dictionary or contains real user passwords like it was cracked database like RockU? Was it generated? Also size matters, and how it can be good for password cracking. There are a bunch of tools like PyPal or PassPal that can give us some useful statistic about word list, like length distribution, top masks, top digits on the end of each dictionary, and many others. But still not anything about is dictionary good for password cracking or not. Maybe some answers about is it junk or not, but nothing about it, about the crack rate. So during my work, I try to make my own statistics, partially based on the information that I can get from PyPal or PassPal, but added some new features like char set distribution, maybe some examples from the word list to see if it's really junk or not, and finally the crack rate. How it was done. So I picked up some hash lists from different sources. There were about 100 of them. Take each dictionary and try to crack each hash list with it. After that, calculate how many passwords can be restored, calculate average value, and this became some crack rate. It's obvious to say that bigger dictionaries always got better results than the smaller ones. So, what if we try to pick up some small dictionaries, make some combinations between them, and to get better dictionaries with the benefits of each other, and it also must be a small dictionary, so why can't we do so? Let's make some calculations. If we have, for example, 10 dictionaries and try to make each combination which contains only 3 of them, there will be no problem. Even if you have 50 dictionaries and try to make combinations with 5 of them, there also we can make it in an hour. But if we try to increase the number of dictionaries or the length of the combinations, the time we need for calculation will increase very fast. So it's then not an answer. To solve this problem, genetic algorithms can be used. So they are good for search optimization and to find approximate solution. In next few slides, I try to describe a basic concept of them and how can they be applied to create better or maybe not word lists. First of all, some theory. In genetic algorithms, we have population that contains of individual. Each individual represented by chromosome. Each chromosome contains genes. So here you can see how it looks like on the paper. And here, some basic process of the genetic algorithm. So firstly, we generate population. After that, evaluate it and try to see if we got individual that are best suitable to solve our case. If not, firstly, we select representatives to generate new to create child, make some crossing, after that some mutation, and evaluate the result children again. After that, we select children that are best suitable and create from them the future population. So let's see how this information can be applied to dictionaries and so on. First of all, gen is a dictionary. It's very important. Each gen contains some set of features. What they are? Firstly, I picked up some training set that contains about 87 hash lists from various sources that can be found all over the internet. And try to crack with each dictionary again each hash list and get some values like the size of the dictionary, how many passwords can it recover, total recovery rate, total recovered passwords, and the unique passwords, the count of the unique passwords that can be recovered using this dictionary. So here are some samples. For top 500 word list. On this table you can see how many passwords can be recovered in each hash list using this word list. For example, for the first one it's 5 passwords and rate is 1%, for the last one is 24 and 4%. Its size is about 44 kilobytes, average recovery rate is 1.8, and total recovered password is 42, and unique password is 24. So what about the chromosome? Chromosome contains gens. So as we know, chromosome contains, because gens is dictionaries, contains dictionaries. So should it be with a fixed number of word list or not? On the first test I choose fixed length of the chromosome. So let's see how it was done and what results I got. First of all, again, chromosome contains gens. As you can see on this slide how it looks like. Each chromosome contains some set of them, and there can be no two similar word lists in one chromosome. It's also very important. For example, this gen contains first dictionary 500 word passwords, and the last and the end of the chromosome is 10, so it's package term dunks. After that, the population was generated. It contains of some sets of chromosomes, as you can see on the slide. So the population generates randomly, so each new test is not the same as previous one. Selection. There are some common patterns for selection. First of all is roll-it wheel selection, where the best fit individual has much more chances to create children than the worst one. And the tournament. Firstly, we select 4 representatives from the population, split them in the pair of 2, and after that select from the pairs representatives that are best, and they create children. Okay, for the first test I use roll-it wheel selection. Crossing. There are also some popular crossing schemes like 1-point crossover, 1-point crossover and 2-point crossover. So we select some border value. After that, chromosomes exchange their gens. It's important to say that the children must have gens from both parents, not only one. So they must be similar to both parents. There are also maybe other scheme where we can randomly exchange few gens between each parents to create children. So, mutation. Each child can mutate with probability of 2%. So how it looks like? Firstly, we select child and randomly select few gens to replace. On this slide is gens 9 and 77, and they are replaced with 78 and 2. Mutation also based on the chromosome length. So for the chromosome length 5, gens to mutate is 1 or 2, and for 20-sized chromosome is 1 to 7. Fitness function. Fitness function are one of the main part of the genetic algorithms. Rely on its value, we decide is our goal achieved or not. So for testing I choose 2 types of it. First, the average crack rate of the dictionary and the total recovered passwords. So something about them. The idea of average crack rate is to get the dictionary that are best suitable for cracking all test cases. And total passwords is to select individual that are best to get more and more passwords. So how it look like on the paper? On the left side of the table in the columns you can see the chromosome with the set of dictionaries. And in the rows, how many each dictionary can crack from each hash list. So we can combine this value and calculate that the total passwords can be recovered with this chromosome is 81, and the average crack rate is about 8%. And penalty. Because I want to get as better as smaller dictionary, there were some penalties based on the size of the dictionary. So there were some border value, for example 10 megabytes. After that, if the chromosome size is more than this value, the penalty is calculated and subtracted from the both fitness values. So the main idea is to make population to bring me the individual that must be as smaller as better to solve my problem. So other options for testing, you can see on this slide that population size for first test was about 500. I tried to also to see if the chromosome size can have some influence on the result output. Number of pairs is 1000 and the dictionaries count is 465. Let's see. Oh, take. The genetic algorithms are best suitable to find some optimum, local optimum, and not the global one. So they easily can fall down to some local value, and it's nearly impossible for them to get to another one that can be better. So if population degrades and the value of the best representative is not changed for some period, there was some shake. It looked like in the next period of mutation, instead of 2%, there were 30%. So the idea is rather simple, to shake the population to get maybe a better optimum. So, some tests were done. On this slide, the first test was used, the limit is 10 megabytes and the fitness function is for total passwords. So on this slide you can see that the population with the chromosome size of 5 dictionaries got the better results than the others. And also you can also see some hops for chromosome size 20 where something happened and the further individuals become better and better than the previous one. So let's see what happened there. I picked up 2 child between the hop. So you can see that they exchanged with few dictionaries, but nothing important seems for me happened. So if we take the last child, you can see that some dictionaries remains from the first population until the end. So there must be something interesting in them, or maybe they really useful. And some core dictionaries, some similarity between population best representatives from each populations with various chromosome size. All the individuals have some similar between each other, some similar dictionaries. So there will be a lot of tables again. So what about this word list? First of all, they have some common in particular. They all have only real user passwords. Some of them are cracked database, like Hellfire or FirstPass. So the way to achieve the better dictionary is to use real user passwords. It's pretty obvious. So another test for 100 megabytes. As you can see, the chromosome with size 20 got better results than others. It's pretty clear that for 100 megabytes, much more dictionaries can be picked up than for 10 megabytes. Some difference between 2 childs. you might see that there are two similar dictionaries like mail out pass and Gmail out pass. They are pretty the same, except one thing, that Gmail out pass has much more user passwords than the mail out pass, so the better child preferred it instead of other. Okay, some similarity between best representatives from 10 megabytes and 100. They all have the same dictionaries. So I may say again that the real passwords in such cases make the deal. Test number 3. Fitness value was changed to crack rate, the 10 megabyte limit. The population with chromosome size from 5 to 15 got pretty similar results, and with the size 20, the results are the same as in previous test. So again, some similarity between them. You may also notice that there are some dictionaries that also exist in test with fitness function or for total passwords. And other test case is for 100 megabyte limit. As you can also notice, there are also some hopes after which the further individuals become better and better. So yes, tables everywhere. Oh, tables. Okay, let's make some comparison between two fitness functions. First of all, they have the similar dictionaries in all the cases. So you can say that the best dictionaries is about top something, XSplit, and zero first pass. All of them contains only a real password. So the most individuals get some core dictionary and try to add other dictionaries, maybe generated one, to create it something new. And okay, let's see some results. First of all, I picked up two maybe best dictionaries is top 1 million and XSplit. Make some another test case which contains about 70 hash lists that are not in the training set. It's very important because testing on the training set is really dull. So what can we see here? That the genetic algorithms allows us to create the dictionary that are better and even smaller than the popular best one. And for 100 megabyte limit, I picked up RockU, popular RockU dictionary, and using genetic algorithms, they allows us to create even half-sized dictionary and the better one than the RockU. It's I think pretty good results. So maybe some conclusions for part 1. Genetic algorithms allow us to create some better dictionaries even for 10%, and the dictionaries are always smaller. But there are some drawbacks. And also, can these results be improved? First of all, about the drawbacks. Correct rate and total passwords are not the same. As you can see on this slide, there is test case 5 that contains only numbers, and dictionary 1 that also contains only numbers. And rely on it, it can get much better total password rate than the other dictionary. So this means that the other dictionary that seems to be better because it has various words. So the test case can really be very subjective and rely on only one test case that are best for one dictionary and are worst for another. The results may be really wrong. And another, the chromosome size limit. I think that it's good for population to decide itself the length of the best individual. And also implant that if we're using only one fitness function, let's like crack rate and total passwords, we got the results that are good in the one particular fitness function, not in the other. It's what it was in plan. So, some improvements. First of all, the length of the chromosome is the size, is the count of the dictionaries. If we have 10 dictionaries for testing, the length of the chromosome is 10. If 20, 20. If 1000, 1000. Each dictionary represented in chromosome by its place. As you can see, the 7 dictionary rotor scan is number 7, and it in chromosome on the 7th place. After that, population was generated. So, first of all, the chromosome randomly generated, so it can has one dictionary, 2, 100, whatever. And the population also generated, so there was some pros and cons. First of all, no fixed dictionary count. I think that's good, but for testing I need really big population size, so it's really hard on calculation for time. And fitness function. So I want some fitness functions that will pay respect for all the fitness values, like crack rate, total passwords, and unique passwords, as they are not the same. I think that using these functions, I can create some polynomial with unknown coefficients that should be found. The one option that the sum of these such coefficients must be 1, that was made for make ratioinating more convenient. So I need to find these coefficients. So I choose some step 0.125 and get that the total numbers, the total result, total numbers of variations are 42. So you can see here some example how the fitness functions look like with these coefficients. So for further testing, I choose tournament selection, slightly increase mutation value, and change the penalty. So on the previous tests, the penalty relies on the dictionary size, and it's not very simple. That's why I choose as a penalty to rely on the count of passwords. It's rather simple. So there was also some border value. After that, the penalty is calculated and subtracted from each fitness value. So the population must brings me the dictionary as small as possible and with the best fitness values. Also, how can these coefficients be found? For this, I make near 50 tests for each coefficients to get as a result to get a dictionary, some dictionary. After that, I make some tests on the final test list, final hash lists, which also contains 17 of them. Calculate the values, make some average of them to see. Make some average of them. Make some average values of them. So this was done to see to remove some randomness. So if I make only one test for each coefficients, I get, for example, that because there are a lot of random, the value cannot be right. So that's why there was 50 of them. And some final results. So I got that using some coefficients, I can get the results that are best in all values, like unique passwords, total passwords, and crack rate. So using them, I try to create nearly 5 dictionaries to see what results I will get. As you can see here, that populations after some time degrade, so there was a global mutation that tried to shake the populations, maybe to get some new values, but it got no luck. and some results. So the chromosome size length for the was get that its optimum size is from 18 to 20, and some comparison between old dictionary test and new one. So you can see here that they are pretty the same. So the dictionaries with real passwords are preferred. And another table, I choose the best representatives from the previous test, and the word list I got its top million in XSplit. As you can see here, one dictionary is even better than the best representatives from previous tests, and of course better than the common popular word list. Slightly better, but it's okay. And another test for 10 million passwords, it's about 100 megabytes. As you can see here, the global mutations helps the populations to jump from one local optimum to another and to get better results. And here the average dictionary size is 35, and there was a dictionary that are even better than the best representatives from previous tests. So, and even better than RockU for about 20%. And some little conclusion. First of all, the genetic algorithms can help to generate some better dictionary in some ways. The test case may be really very subjective, so that's why there were a lot of them. The bigger dictionary is not always better because the speed is really critical, and real user passwords are more preferred than generated one. And also, by this link you can find some results that we made during these tests. I think this is the end. If you have some questions, you might ask. Yep.